do this, I just get a feeling that it might be a good idea. So I want to finish off section 15 by doing 2 more examples. One, we have talked about finding the volume of a solid, and the second one we haven't talked about, which is how do you find the average value of a function. So finding a solid, let me find one. Finding a solid. Can't be too far away. There, this one. This one is like question 16. We're trying to find the volume of a solid where z is 7x squared, and the region D is described by y equals x squared, the plane z equals 0 and y equals 4. Well, the plane z equals 0 is not really that important because that's basically the floor, right? That's the xy plane, which is typically where we do these things anyway. So if you put these two together, you get a y equals x squared and you get a y equals 4. So here is D. So here's y equals 4. So to set up, what will the volume look like? Well, the volume is the double integral of a function over the region D. It's a double integral. This guy here is the function, and this region is our guy. So there's going to be a 7x squared goes here. Okay, I want to build this region up. I want to create D. We can go X's, we can go Y's, we can go type 1s, we can go type 2s, however way you want to phrase it. But in some questions, only one direction works. Would it make sense to do vertical rectangles or to do horizontal rectangles? That's your question. Which direction is the only one that actually works?
Vertical?
Yeah. And the reason why vertical works is, isn't the top a straight line and isn't the bottom always a curve? If I tried to go horizontal, wouldn't the top be a curve and the bottom would be the same curve? That is a big no-no, right? You can't really do it where the top and bottom are the same curve, right? The math just doesn't work out nice. So in this case here, since we're going this way, don't we need to know here and here, right? We need to know what the x values are. Well, I know y equals x squared, and I know that y equals 4. I guess if I put it into Desmos, I could find out. But it's pretty easy to see it's plus or minus 2. So I'm not even using Desmos. So x is going to be minus 2 to plus 2. And then it's going to be from bottom to top, that guy there. At the bottom, the y thing is equal to the curve. And at the top, it's equal to 4. And we're going to do the y's, and then we're going to do the x's. Are you comfortable about how this double integral that's going to find the volume of this shape was created? Right. Can I just say ... because you've probably done enough double integrals in your life to finish that off, right? I think the vast majority of these double integrals have been eventually polynomials, haven't they? There've been maybe 1 or 2 sines and cosines floating about, and I think we've had an e and x cubed once as well. So you typically don't really deal with horrible things to integrate, right? They're pretty standard things. Construction is where all the work is. We good with this one? Can I move on? Okay. Now,
I'm good.
Okay, how to find the average value of a function? Well, it has to be an average value of a function over a region, typically. And here is the weird notation that we borrowed from Calc 2. It is equal to 1 over the area of region D, the double integral over region D of our function dA. So I believe there are two examples of this one. One is a triangle and the other's more interesting. So this is going to be similar to question 60. Our function, our z function, is going to be 4x cosine y. And the region D is y equals 0, y equals x squared, and x equals 2. And we are going to find the average value of this function in that region. Okay, so first thing I'm going to do is sketch what the region looks like. Since we're talking y equals 0, we're talking this axis, y equals x squared, talking this guy, and x equals 2, we're talking this guy. I'm assuming, I may have misread something, but I'm assuming they're talking about that guy. Seems reasonable. So my region D is here. Now, since this formula needs to know the area of D, then I'm going to have to find the area of D. Well, isn't that the integral from 0 to 2 of x squared? You agree? The area of this region, but a good old-fashioned Calc 2 area, right, is the integral from 0 to 2 of the function y squared, which is this fella, which is 8/3. So that wasn't too hard to get. Now we can get the average value of the function. It's 1 over the area, which is this fella, the double integral, which I haven't created yet, and I guess I should have, of 4x cosine y. Right. If I look at this particular shaded region, I can go up and down, right, vertical. I can go left and right, and both will work. I'm pretty sure at least both will work. I'm going to do vertical. So the region D then is going to be x going from 0 to 2 and y going from 0 to x squared. So x is going to go from 0 to 2 and y is going to go from 0 to x squared. And I'm going to go y first and x next. Okay, 1 over 8/3 is just the same thing as 3/8. If you integrate 4x cosine y with respect to y, don't you just get 4x sine y, right? 4x cosine y gets you 4x sine y with respect to y. Evaluate at 0 and at x squared. If you plug in x squared here, you get 4x, the sine of x squared. And if you plug in 0 here, sine of 0 is 0, so you get nothing. And you're at this stage here. Are we comfortable with that? Okay, I'm going to dot this. This is a Calc 2 question, agreed? What method would I use to integrate 4x sine x squared?
U substitution.
And the U sub would be x squared, agreed?
Yes.
And your answer will look ugly, but it will be correct. What do I mean it looks ugly? You will have things like 5 sine 1 minus 3, right? There'll be a sine 1, which looks awkward. You're used to sine pi over 3 and turn it into a number, right? But when the value of the angle is not a standard angle, like x is 1, you get the sine of 1, then that's your answer. Just leave it alone. So you could get questions with sine 4 or cosine 3 in it for the same reason. Because, you know, in WebAssign, this will turn into a sine or a cosine, or this will turn into a 2, or, you know, they muck about with it. So that's okay. So don't talk yourself out of an answer because it looks like 4 sine 1 minus 3 or something, right? Are we comfortable with the process of how you find the average value? Find the area of region D, and then do a normal double integral. So if it wasn't for that 1 over the area of D bit, wouldn't this just be a normal double integral question? It really is. So you just get an extra little step at the start. Apart from that, same old, same old. Right, are there any questions about that section before we move on to our next one? Okay. And this one is going to be using polar coordinates. Basically transformation. When you do double integrals, the region D so far has been nice rectangles, which was what 15.1 was about, or it has been triangles, you know, x squareds and, you know, x cubes. It's been shapes that are basically curves or straight lines. What it hasn't been for the most part, or at all, is circles. So 15.3 allows us to find double integrals when the region D is a circle or a part of a circle. And apart from that, we have to do a change in variable essentially. So your function will be given in terms of x and y, but we will turn them into polar. Now, if you remember way back in the day in trig, polar is a different coordinate system. It allows you to tell a position of an object in 2D space by using r and theta, which, just to tell you, if I wanted that point there, whose coordinates were x, y, if you wanted to describe that same point in polar, you would tell me the distance from the origin, called r, and you would give me the angle from the x-axis, and you'd call that theta. Does that ring some bells, polar? Now, here's something that might be a bit rusty. Does anybody remember what the x coordinates are in terms of polar variables, r and theta?
Is X R cosine theta?
No, it's cosine theta. Keep going. And why?
Y sine theta?
You just can't force yourself to say it, can you?
I cannot. Is it theta?
Well, no, Americans call it theta, and it's one of my many bugs. It's theta. Had not an argument really. Me and my wife don't have arguments in that sense, but we had a good discussion on how do you say it properly, and I figured out that I can understand a little bit why Americans don't know how to say Z, right? Because you've had so many other European, at the beginning at least, European influences, you know, Spanish and Italian and all sorts of other countries, that might have influenced your pronunciation of some of the letters of the alphabet. But I do not know how you managed to screw up a different country's letter, because it's Greek. Right? And they call it theta, I believe, I hope. So where did this theta come from? You can't tell me, can you?
Americans are pretty good at messing stuff up.
You know that when you used to be British, because there was a time when America was British, right? You weren't always America. You used to be a British colony. When you were a British colony, you used to say theta. I can't imagine that you crossed the boat and then when you got off the boat, suddenly you started saying various letters of the alphabet differently. So I'm assuming that you said it the same way that I would say it. And then you hit America and you start changing things. You are a weird lot. Okay, X and Y. There is another relationship that is very useful. And it is that X squared plus Y squared equals R squared. So we're just going to build up some skill building exercises here on changing X's and Y's into R's and Thetas, and get used to that. So if D was an entire circle and its radius was 3, right? D would now be in polar form the following. To create the entire circle, including all the points inside it, won't you make R from 0 to 3? Right, a start value of 0 would be the origin, and then you pull out to the end as 3. And wouldn't the angle start at 0 and rotate round to the beginning again, which is 2 pi? That is what a complete circle of radius 3 looks like. Does that seem reasonable based on the way you describe things? So we are going to have to get used to taking shapes and rewriting them in terms of R and theta. Because once we do that, and we turn all the X's and Y's into these guys, won't we just have a double integral again? But instead of we X's and Y's and dx and dy's, we're going to have R's and thetas and dr's and d thetas, right? So it'll be just basically like a change in variable. So still practicing or getting used to this one.
I believe Travis has a question.
Oh, what's your question, Travis?
Could theta ever be more than 2 pi? Like
Not really, because you're just circling back on top of the thing. So the convention is once you've done the shape, stop looking.
If it was like a helical shape or something, would it or could it go past that?
Well, a helix could, but this shape is in 2D and it's the floor, it's the XY plane. Okay. And because it's a single disk in the XY plane, helixes don't exist. Right. It's basically just a region. Now, helix would go upwards like Calc 3, but this is what we have. Right, let's suppose this is -44 and I want this region. So we need to know what R does, and we need to know what theta does. What would be the range in values for the R variable to create this half disk?
Just be 0 to 4, right?
Correct. What would the theta be to make that disk?
0 to pi.
Pi.
Agreed. This one catches people out. Not this one, the one I'm about to do. Now I'll do the first part. The R still goes from 0 to 5. What is the range in theta?
Half pi to 3 over pi.
Well, if you did a half pi to 3 over pi, you would actually create this disk on the other side.
Minus half
So-
pi to half pi.
Agreed.
The other side of the circle.
Yes. So you would need, do you see in this case, negative thetas can happen, right? Let's try a different orientation. What would get you that guy?
Could you call it pi to 2 pi?
I would. Could you call it negative pi to 0? Yes. That would have the same effect, but I would choose pi to 2 pi. Well, we've pretty much broken a circle into various pieces, which is nice, but we can do better. I want this donut shape called a torus. Any volunteers?
That would be, I'm gonna say 2 to 10 for the R.
Right. Yeah.
And then the theta will be
0 to 2 pi, right? Because it's an entire revolution.
Yes.
yeah.
Now, I'm not going to go through all the permutations, but could you imagine I could take that and have an inside piece? Right. This would stay the same. If I use this one, but I curved it that way, this would stay the same, right? The R value would change, right? You have to have an inside radius and an outside. But when you do one of these donuts, torus shapes, you know, a circle within a circle. Imagine I gave you that as a double integral at the start of today. Can you see how horribly ugly it would be to try and describe that using X's and Y's? I mean, it would be
Terrible.
I'm not even sure doable. I mean, I guess you could break the shape up into various pieces. In other words, break your D into various pieces and do a double integral for each piece. I guess you could probably get away with that. So you might just break it into that little piece, you know, 1, 2, 3, 4, and figure it out that way. But horrible, horrible math. And can you imagine that the equation would probably be something like y equals the square root of 100 minus x squared, which is what the rearrangement of the equation of a circle would be. You do not want to start sticking things like that inside integrals, because won't even the integration become ridiculously ugly? So I'm trying to sell you that there are some circumstances, essentially circumstances where circles, bits of circles, or donuts are involved, where converting into polar coordinate system just makes sense, right? It makes it easier to do rather than sticking to the X's and Y's. So now we are ready for how do you do that? Well, a double integral over a region D of some function f of xy dA, where dA is either dx dy or it's dy by dx, right? We recognize that that's just a placeholder, isn't it? Because sometimes you do x first, sometimes you do y first. So dA is a differential over an area, right? This is equal to, so I'm going to have to do it this way, the double integral of d of f. Instead of the x's, you replace all the x's with r cos theta. Instead of the y's, you replace them all with r sine theta. You don't have a dA anymore. What you have is an r, yep, an r, a dr, and a d theta. Or an r, d theta, dr, if you want to switch it the other way around. Now you might say, where on earth did this extra r come from? Shouldn't it just be dr, d theta? I want you to think a little bit like, can you imagine I did a u sub? And you know when you do u subs, you get extra bits left over. It's the equivalent to that. You're just going to have to trust me right now, but we are going to be doing later on double and so on, multivariate differentiation, where we will be doing change in variable, right? Essentially u subs. And they're called Jacobians when we do those. When that happens, will you remind me and I'll prove to you why that r should be there, right? But right now, you're just taking it for granted. Right? So if you take a question that involves a circle or part of a circle, and you want to find its double integral, this is your go-to guy. Now, the region D is the same, but in here isn't D in terms of X's and Y's, but won't the D be the guys we've been doing with R's and Theta's in it, right? So keep that in mind. So I need to find, if you pause a minute, stop this fella. I need to go in and go here and go. Here is polar. Right, I'm going to show you what some of these questions look like, then we can start doing them. What button do I press? I press this one, don't I? Okay, so here is WebAssign homework for 15.3 up and running. You're going to find the integral of 2xy squared, but d is the top half of a disk. Right, so that bit, right? And we'll get its integral. Here is your function. This time the region R, okay, they're calling them RD, who cares what letter of the alphabet they use. It's in the first quadrant using that circle. And a little line called y equals x, that'll be interesting. Here's our function. First quadrant, a circle. Oh, it's a circle between 3 and 4. Do you know one of those donut shapes? It's one of those, but it's only in the first quadrant. This one we'll worry about when we do it. This is just a basic circle, radius 8. Here is two weird shapes that we'll talk about when we need to. Oh, okay. Well, that's for tomorrow. I don't want to get too far ahead of myself. So, I mean, the basic theme here is that the region D or R, whatever letter of the alphabet they're deciding to call it, has something circular about it, right? It's a donut, it's a half circle, whatever. Right, so this is my version of question 1. And we're going to do a double integral over d of 2x squared y dA. And d is the top half of a disk, which means that, and the radius is 5. So there's d. So far, so good. Nice, straightforward one. You get the job moving. So let's see what we can do about the Scylla. The region D.
We can see your screen, Professor.
You were just going to let me rant on for 10 minutes, weren't you? Can't take you lot anywhere. There we go. So this region is now going to be using r and theta. The r values are from 0 to 5. And the theta in this case is from 0 to pi. Are we comfortable about the polar version of that region? R goes from 0 to 5, and theta goes from 0 all the way around to pi. Now, the double integral that we're going to do here is from theta equals 0 to theta equals pi, r equals 0 to r equals 5. And this function becomes 2. I should probably put this over here. Two x squared becomes 2 r cosine theta squared, or sine theta. And then remember that extra r. I don't know how many times I keep forgetting that little r myself, right? You know, that little r that you just trust me on. Now, what I would do in this question here is some style points before I even think about integrating. So that's 2. That's r squared cos squared. That's an r sine. There's another r dr d theta. I think I could still do more. One, two, three. That's 2 r to the 4 cos squared theta sine theta dr d theta. Are we okay so far with the style points? Just putting things together, collecting terms. Everything's been multiplied by something else, so we've got a single big multiplication. Now, I know this isn't x's and y's, but x's and y's are just letters of the alphabet representing variables. Here we have a variable called theta, and here we have a variable called r. Would you agree that these are all numbers? So it's very similar to what we did in 15.1. Secondly, are these separable?
Yeah, aren't they?
Yeah. And if things are separable, do you know it tends to be less work if you do it, if you separate them? So in this case, I will do that. I will do theta equals 0 to pi. I don't know. Who do you want to give the 2 to? Do you want to give it to the r to the 4, or do you want to give it to the thetas? I have to give it to somebody. Guess it doesn't really matter, but what do you want?
To the r to the 4th. I feel like it's less of a hassle on there.
Okay, then we'll do it that way. Now, what we've essentially done here by separating out the integral is, haven't I now created two Calc 2 questions? I got this guy and I got this guy. Now, I don't have an awful lot of room, so I'm going to do each one kind of over here. So from 0 to pi, cos squared theta, sine theta, d theta. Let's do that one first. Okay. What technique will I use to integrate this fella? Again, it's a Calc 2 problem.
U sub would work.
It would. Who's the U sub?
The cosine.
Correct. So du by d theta is differentiate, so it's a negative sign. The crossover. And then you isolate the d theta. So my integral will now become, instead of cos squared, u squared. I'll leave the sine theta for a minute and replace the d theta by that. Which gets me that, which is really nice because it's simply just negative 1/3 u cubed. Then I return it back into its thetas and evaluate it at 0 and at pi. U sub, integrate, return back to theta, put your limits of integration in. This is going to be 1/3 the cosine of pi being cubed, take away negative 1/3 the cosine of 0 being cubed. Okay, cosine of pi has an exact value. It's -1, I believe. So it's -1 cubed. And cosine of 0 is definitely 1. -1 cubed is -1, makes that a third. Take away another guy who's also a third, and you end up with 2/3. So 2/3 goes there. And we've done half the problem. Can you imagine, just by the way that these things are created, aren't you going to be doing quite a lot in the theta world? Sines and cosines and u subs and trig identities and whatever, right? That's the kind of skill set you'll be doing there. On the other hand, for the most part, aren't the R side just going to be power rules? R cubes, R squareds, R to the halves probably. So let's do that one now. Add 1 to the power, divide by the new power, evaluated at 0, evaluated at 5. That's 2/5, or, 5, e to the 5, take away nothing. It's 625, that's 1250. Ooh, that's a big answer. Which gives me 2,500 thirds. Not one of you argued about that answer. I did that in my head and you just wrote that down. Has anybody tried to even check it?
My actual question is, then to get the final answer, we multiply these two values again?
Correct. Yes. Which is what's happening here. 2/3 was the first one. 1250 is the second one. I'm assuming that's 2,500 thirds. Right, back to this one. Is that right? Aren't you impressed that I did a mental calculation that's as ugly as that and I got it right? I should do the lottery today. But anyway, that's what calculators are for, so it's not a biggie. Do you get a feel, I know it's only one example, but do you get a feel for how these questions are going to progress, the kind of the process that we're going to use to make them happen? Okay. I think, yeah, there are only 10 questions, so I'm going to have to be quite selective about. Oh, I need to put this one in. We're going to do the double integral over some region R. Why they don't call it D, who knows? It makes no difference whatever you call it. 2x take away y, dA. What we know is that this shape is in the first quadrant and that it's x squared plus y squared is 16, which is just another way of saying that. And it's x equals 0, which is this line, which isn't a big deal. And then it's got a line called y equals x, and that is a big deal. Because this is the first time we've had to deal with a piece of pie shape. Doesn't that look like a piece of pie? Agreed? And I have to figure, we have to figure out how to describe that region. Well, let's focus on the R value. I know you've got this diagonal line going here, but it really doesn't affect anything. Isn't the R from 0 to 4? Right. The theta, however, is a little bit sneaky. This line y equals x, what angle does that make with the x-axis?
45 degrees.
And degrees, it is 45, and I'm just going to convert it into radians. So this line going that way has a theta of pi upon 2, and this straight line has a theta of pi upon 4. Does that make sense how we created that particular combination? Okay. So we're going to do a double integral then. The R values are going to go from 0 to 4, and the theta values are going to go from pi upon 4 to pi upon 2. We have 2 times x, which is r cos theta, take away y, which is r sin theta, and the dA becomes an r, a dr, and a d theta. So far, so good. Now I'm going to do some style points on this. But not the kind of style points you might be thinking about. You might think I was just going to distribute that R, which would be quite sensible, but I'm not. I'm actually going to pull this R out as a common factor and multiply it by that, and I am going to get R squared, 2 cosine theta, take away sine theta, dr, d theta. Why do you think I've decided to do the style points in this form instead of just multiplying it out and have 2 terms?
So it's separable?
Yeah.
Professor,
Now,
I have a quick question.
yes.
So my question is regarding the limit of the equation that we're taking it against. So shouldn't be d theta times dr, or it doesn't matter?
does matter because of what I've just written there,
Okay.
but I'm going to be separating them out in a minute, so I would have fixed it.
Okay. All right.
So it does separate. Now, I'm not going to say that you'll be able to get, variable separable in these, but anytime that you do, it's a good idea, right, to do it. I won't take this guy to the end, but won't he be a 1/3 r cubed, r equals 0 to 4? Great. And this guy here, he's going to be a 2 sine theta plus a cosine theta, evaluated at pi upon 4 and pi upon 2. And then this guy times that guy, and you're finished. Maggie, I'm busy. Whoops. Give me a moment.
He just wants to learn.
Our dogs needed a poo walk. That was Maggie. She's the sick one. You wouldn't think it. But my wife's doing it, so that's good. Am I okay doing the ... here? Are you pretty comfortable? It's just time consuming, plug in some numbers. Are we good? Last chance, moving on. Oh God, look at the time. We all say hi. And
Done.
we are done. I'll hang about if anybody's got some questions. Otherwise, I will see you tomorrow, where, with a bit of luck, we will finish Ola.